Recent advances in technology have transformed the way we gather and store information. Today, anyone with an internet connection can access myriad types and quantities of publicly available data, from enormous global trends to minute changes in the genetic code. This increase in data accessibility has led to great scientific advancement for problems with a single root cause. Sadly, the public health problems challenging our society today are complicated, multifactorial issues, and require more than just data access. These challenges necessitate disparate complex data sets and researchers of varying domains. CMOS, an open-source software developed by Deloitte, seamlessly merges the three major components of the data analytics process: data federation, visualization, and analytics, all three extendable and customizable by an experienced team of CMOS developers. According to expert opinion, the process of loading data can often account for up to 80% of the entire analysis process. With automated data normalization and structuring, CMOS greatly minimizes the traditional tedious loading process. In many ways, CMOS is a hypothesis generation engine, allowing researchers to connect into an ecosystem of public government data with their personal, private data while retaining full data privacy controls. This allows user intuition, not technical limitations, to drive the research process. To explore these captivating capabilities, let's begin with the United States Department of Agriculture dataset and see where it takes us. Our table extracts the United States counties from the data and lists over 100 associated variables on the left panel. First, we add the adult obesity rate variable, measured by body mass index, which instantly links to each county in the table. Imagining we are a housing and urban planning economist researching how access to healthy food affects obesity, we select another variable, like households with no car and low access to stores, as a percentage of this county. Next, let's add a more common variable, like median household income, and use our domain expertise to filter to New Jersey and Alabama, two states that historically have had dissimilar obesity rates. Using our selected data, let's build a scatter plot looking at bubbles for each county to see the association between the obesity rate on the x-axis with higher rates to the right and percentage of residents with no car and low access to stores on the y-axis with less store access as we move upward. We already notice an interesting trend here, which we can explore further by attaching median income as the bubble size. The wider the bubble, the higher the median income. Finally, we can add color to the counties of the two selected states to observe the stark difference in obesity across states, even as the trend of car and store access holds stable. If we like this visual, it is easy to save and share with our social network. Now that the question is saved, in just one click we can switch to a different visualization or analytics routine. Let's look at a matrix regression to calculate the line of best fit for this data. Here we see obesity in the left panel with body mass index indicating along the y-axis, which applies to all three visualizations. In each plot, the higher the county data bubbles, the higher the rate of obesity. In the middle panel, we have household car ownership and store access, with each bubble still representing the prior state counties. In the x-axis, bubbles to the right indicate residents with less car or store access. As well, we see the calculated correlation to obesity for these data at the bottom. The right panel shows the median income of each county. Income rises in county bubble to the right. To explore this data at a deeper level, we can highlight county bubbles and see the same counties in the other plots. For instance, we select only those counties with the lowest median incomes and immediately notice they fall into highest obesity rates and lowest rates of car ownership and store access. Then as we move the slider to the right, highlighting the counties with higher median incomes, we see the impact of lowered BMI and increased car and store access in the middle panel. As this work continues, an environmental scientist at the Environmental Protection Agency from our network observes the shared visualization. This spurs the inquiry to explore obesity in population by adding Google Maps and Environmental Protection Agency's Air Quality Index report to build a layered interactive map visualization. Here we plot each county on the map, with the size of each bubble representing the rate of obesity in that county and the color representing the number of days of poor air quality. Immediately, California stands out. If we really want to dive in, we explore the map at any level of detail using a satellite view. The ability to connect, filter, visualize, and collaborate in one platform with researchers from disparate fields empowers the analysis of complex multifactorial problems like obesity. By reducing the barriers typically associated with gathering and loading data, CMOS allows researchers across multiple organizations to hypothesize rapidly, conduct robust analysis, answer questions, and share results in one collaborative platform. This, by accelerating scientific insight and discovery, will potentially make obesity a thing of the past.